Hello, everyone. We'll be starting in about a minute or so, top of the hour, for the next installment of the PCB webinar bootcamp series. Please feel free to get used to the interface. If you would like, please in the chat box, let me know where you're joining us from today, and we'll get started in about a minute. Oh, great. We have people from all over joining us. I see some from Montreal and Quebec. We have Huntsville, Alabama. A few people in Austin joining us. Great. Thank you so much, everyone. Switzerland. Wow, that's great. So, it is now noon. So I'd like to welcome you all to this installment of TTM Technologies 2019 Bootcamp Webinar Series. We post all of our upcoming webinar information to LinkedIn, so make sure you're following us so you don't miss out. Today, your guide will be Senior Field Applications Engineer Gus Trackus. Gus will provide an overview of the PCB raw material manufacturing process, production, we'll be going over the different materials used for the manufacturing process. Gus works with the Automotive, Medical, Industrial, and Instrumentation Business Unit and is based out of Toronto, Canada. Throughout his career, he has gained experience in process engineering, quality, and now works directly with customers to provide design for manufacturer and other guidance. These days, Gus spends a lot of his time on exciting projects for autonomous driving, electric vehicles, advanced safety, and other high reliability applications. My name is Sarah Casey, and I'll be your host today. I work for the AMI&I business unit with Gus, and I'm also housed out of Toronto facility. With me is the fabulous Angie Kerr, one of our top customer service representatives out of Logan, Utah facility. Angie has extensive PCB experience and makes sure that this session runs like clockwork. We couldn't do it without her. A few housekeeping items before we dive into the good stuff. This webinar will be made available as an on-demand recording. An email will be sent to all registrants with instructions for accessing the recording within 48 hours of this session's conclusion. Our recordings are now interactive, so you can ask questions and we will channel your questions to the appropriate TTM representative to make sure you have all the support you need. The PDF version of this presentation is available for download in the handout section of the GoToWebinar interface. Please take a moment to download the material. We will also send a link and a follow-up email with access to this PDF. All participants are muted by default. And lastly, for questions, please type your questions into the field provided by GoToWebinar's interface. If we don't get to your question during the presentation, don't worry. We'll reach out to you directly afterwards. As soon as the presentation over we'll go straight into the question and answer. Without further ado, please welcome Gus Trackus. Gus, take it away.
Thanks, Sarah. And again, thanks everyone for attending. I'm going to just flip my screen here so that I'm in charge. Get you all on a slideshow. All right. Okay, so before we start, always a couple of quick items to inform everyone about. So first, TTM has both commercial and ITAR-based printed circuit board solutions. This specific presentation was developed with a commercial customer in mind. As always, please reach out to the TTM team if you would like more information for non-commercial applications. And then second, a reminder that the material contained in this webinar is considered proprietary and confidential and should not be distributed outside of your organization. All right, let's begin. Today we have a lot of slides we want to get through, so we're going to start. Today we'll be focusing on PCB materials And when we look at factors that influence material selection, we look at items like electrical design, things like dielectric constant, loss tangent, other variables. We look at items related to reliability. So can the materials survive lead-free assembly, long-term service life, CAF considerations, and if you're wondering what CAF is, stands for conductive anodic filament. And coincidentally, our next webinar in April will be on the CAF topic. And then finally, thermal mechanical properties, items like X, Y, and Z, thermal expansion, TG, TD, and we'll talk about all these parameters as we go through. So let's begin. Our agenda for today is the following. We'll start off with a primer on material manufacturing, basically what our suppliers make for us. And that includes prepregs, rolled annealed copper foil, electrodeposited copper foil, general construction of laminates and how it's done. We'll look at thermomechanical considerations. We'll spend some time on electrical considerations, and finally, we'll sum it all up when we're done. All right, let's start off with basics of materials. When we look at typical FR4 or other laminate types that we are using in our process, there's basically 3 components. There is copper foils, there is woven glass fabrics, which consist of bundles of glass fibers interwoven to create some reinforcement in that build, and then also a resin. And the resin typically is the IP of the material manufacturer. Most common resin what we work with is what we call FR4. And in terms of the resin itself, it comes in 3 forms. There's what we call A stage, which is a pure liquid form, B stage, which is a partially cured resin, often called prepreg, and then there's a C stage, which is the fully cured resin, which we often see in laminate materials, or in the case of a fabricator, a fully pressed circuit board. So to start, our supplier's supplier, so 2 steps up from us, will create glass yarns, they'll take glass yarns and they'll use them to weave glass fabrics, and they'll do this for all different constructions. And as we go through, you'll see there's different glass types, different glass thicknesses that are all interwoven to create the final structure. And in terms of glass types, there's your standard E-glass or electronic grade glass, which has a certain subset of chemicals in it that form together to create the specific material properties. There is a high strength or S-glass version of this. Again, different proportions of chemicals to create different material properties in the final product. And then there's also glasses that have improved electricals and mechanicals. So a common one would be like an NE glass. And you look at the properties of these materials, again, different sets of properties. And if you look at the bottom of this table on slide 8, you'll notice that each one of these glasses have different coefficients of thermal expansion, different dielectric constants, and different loss tangents depending on what's required for that specific material set. So our supplier will take these glass fibers and they will weave them, kind of like textile manufacturing in a sense. They'll weave them into large rolls of glass fabric, which they will then send out to our material supplier for them to create the specific materials that we'll be using in our process. Now, one thing to note is these things, or these bundles, are woven, and the fabricator will stretch a set of bundles in one direction, and then they will weave through the other set of fiber bundles in typically a 90-degree fashion in order to create that weave. And if you look at the picture at the top right, you'll notice that there is actually a direction to this glass. So there's what we call a warp direction, which is the direction that is being stressed, or a tensile direction for the glass. And then we also have a fill direction, which is what's woven in between these this first of stretched fiber bundles. And you'll notice again, one of these directions appears to be under tension and the other one does not. Now, that is important for us to know, because when we build circuit boards, materials tend to move, and they actually move differently in, let's say, an X direction versus a Y direction in terms of both movement and also shrinkage and growth as we're building this. So from a fabricator perspective, we need to understand when we receive material from our supplier what the warp direction is and what the fill direction is of the reinforcing glass within that laminate material. So we have different glass styles, and the glass style, and I get asked this quite a lot, is what do those numbers mean? Well, here's sort of what they mean in terms of how they translate to how many glass strands in the X and the Y direction, and also how thick the glass is, and also the thickness of the specific weave itself. So there's some numbers here that show some standard glass styles like 106, 1080, 2116, all the way up to 7628, and those are all acronyms in a sense that tell us what the glass thickness is of that mat, and then also what's used to construct the glass mat itself. Just taking another look at this from a more microscopic view, you have, for example, glass styles like 106, which is what we call a very loose weave. So in the top left corner, you'll see that there's the glass bundles going in the X and Y direction, but there's a lot of gaps in between those bundles, which is normal for that weave of material. And then as you go through to 1080, 2113, and all the way up to 7628, the glass bundles tend to get thicker, and then the spacing between the glass bundles tends to disappear as the weaves get larger and tighter. Okay, and this also plays a role for signal integrity, because what we see is a discrepancy between, I'll just skip back here. We see a discrepancy between the properties for dielectric constant and loss tangent for resin versus glass, and that can become a big issue at higher speeds. So knowing that, glass is also available with different what we call spread characteristics of it. So the picture on the left shows a standard weave 1080, which has a lot of gaps between it, and the picture on the right shows a 1078, what we call a spread glass weave. That is, in this case, it's mechanically flattened in order to remove the gaps between the bundles. Now, I show here a couple of theoretical differential traces, and what we see on the image on the left is one trace tends to run completely over a glass bundle, whereas the other trace tends to run over an alternating glass and resin feature underneath it. And again, that can become a big problem as we get to higher speeds. And I'll talk a bit about that more later. Now, we take those glass bundles and we pair that with a resin system. And there's different types of resin systems. So there's the classic, what we call tetrafunctional resin system, which also is typically known as a low TG material set. And then as we progress into materials that are more capable of surviving lead-free processing, we get to higher TGs, and the material composition or the plastic composition of these materials tends to become a little more involved. So we go from tetrafunctional to multifunctional to enhanced multifunctional, where the supplier is adding additional ingredients into that mix in order to get that glass transition temperature higher. And then finally, what we have a cured phenolic filled epoxy. All these are just different resin types. But what's important is we look over to the right side of the column, we see CT in the Z-axis, and the lower, I say lower quality, but the lower TG material sets typically tend to have much higher Z-axis expansion than the ones that are higher TG. And that's important for when we are looking at expansion of materials. But continuing along with just the basics of how we build this, so our supplier has their IP, which is their specific resin. They then take the glass fabric that's supplied to them in those rolls, and then they coat that glass fabric with the resin material. So in this picture here on slide 15, you'll see a blue tub That's the resin, and then the glass fabric gets rolled into that, where it gets impregnated with the resin material. That's sent off to a cooling tower to cool down, and then it's rolled up into a roll that's now called prepreg. So these large sheets of prepreg get cut down into a form that we can use, because we're going to take this prepreg and we're going to use some of it to bond our stack ups later on. But then that prepreg is also taken by our supplier, and they're going to go ahead and combine it with copper foil to create cores for us. And on the copper foil side, there's two options. There's electrodeposited foil, also known as ED foil. Then there's rolled annealed foil, which we call RA. And rolled annealed copper is the one that is less used. It is used primarily for flex materials because its properties allow it to have higher elongation and higher tensile strength, which is great for bending. It's also used a lot for microwave applications where it's just a lot flatter, and it provides better roughness values for use in high frequency circuits. The only thing to note with these two is rolled annealed foils are not always available on all material sets, so be careful if you're trying to spec it out in conjunction with, let's say, an FR4. Likely it's not available in that combination. But let's go through and let's look at how each of these foil types are made. So the first one we look at is the rolled annealed process. And in this case, the foil manufacturer, which is not our material manufacturer, the foil manufacturer will take large slabs of copper and successively roll them under very heavy rollers into a more manageable thickness. So as it goes through these rolling sets, it gets a little bit thinner. And then finally, it gets to that thickness of foil that they're looking at. So whether it's 1/2 ounce foil, 1 ounce, 2 ounce foil, they can set the parameters of the rollers to get the final desired thickness that they want. Also to note, because it is traveling in a direction, it does have a grain direction to it. So just good to know that. And then like we mentioned, it is very beneficial for flex because of its properties in terms of elongation and tensile strength, and also for microwave because it has a fairly flat and smooth finish. Now that flat finish doesn't always do us good from the lamination perspective, because the flatter the foil is, the less teeth it has to bond. So it will not bond as well as, let's say, a typical electrodeposited foil, which we'll talk about later. So just be aware of the fact that peel strengths typically are a little bit less than they would be for what we call standard electrodeposited foils. Now, if we look at the more popular one, the ED foil. So with this, the supplier will take basically copper wire. They will dissolve it in a big vat of sulfuric acid, and they will then create copper sulfate in solution, which is that blue liquid. Then they're going to go ahead and place that liquid into a big drum or into a big a vat, and they're going to attach a drum to it. Now that drum is going to be electrified. And going back to basic chemistry, if we take copper sulfate in solution and then we add electrons to it, we're now able to create copper metal from that. So using a big rotating titanium drum, they're going to take that, rotate it through the copper solution, and that drum has a current applied to it. And then what comes out the other end is essentially copper foil. So the copper foil gets deposited, or the electrons get deposited as foil particles, which will then accumulate and agglomerate into the final foil structure. And again, that can be controlled in terms of how thick that foil is going to be created. Now, if we look at the microscopic view of what's being created, there's always that drum side, and that drum side is the foil that is up against the smooth titanium drum. And as you would expect, the foil has very smooth properties to it. And then the other side is a lot more matte in structure. So the foil actually, or the copper actually grows out in a columnar fashion. So it grows out in columns from that base of that drum all the way to that final thickness. And then what we see is, if we look at it from a microscopic level, we see a lot of bumps and valleys, which is great for bonding on our side, but again, not always essentially a good thing on high-speed applications. Now, if we look at that that structure that we created, even though one side is rough, we still need to add additional topography to that in order to get that to bond, and that's being done by our foil manufacturer. So they're going to treat both sides of that foil. So even that matte side that's already pretty rough, they're going to go ahead and treat it and create additional copper crystals on it to make it even more rough for bonding. And they're going to go ahead and do the same thing on the drum side. So they're going to take that drum side foil, which is very smooth. They're going to treat that as well. Basically, they're going to attach copper nodules to it. They're going to go ahead and encapsulate it with zincates and chromates and silates, and they're going to create a rough surface on that drum side as well. So they're actually treating both sides, and then one side will end up being pressed onto their resin. Then the other side will be provided to us, the PCB manufacturers, as is. And in terms of what side they press where, it all depends on what you're ordering. So typical DSTF foil, which stands for drum side treated foil. So they're going to treat that and apply that to the shiny side, and that is going to be the surface of what that core would be. So they're going to bond the matte side to the laminate material. For reverse treated foil, very similar. And then also they have different options in terms of the roughness value of those foils that they create. Now, like I said earlier, the rougher it is, the easier it is to bond. So as foil manufacturers realize that the foil has to be smoother in high speed and high frequency applications, they're trying to get these things as smooth as possible, but also still be able to bond them onto their laminate that they're supplying, because at the end of the day, there still is a peel strength value that we have to meet as fabricators to ensure that what we're building doesn't have that copper just come right off, let's say after assembly, for example. And then as we increase in terms of, I would say, quality of foil, and then the foil roughness also starts to become a lot thinner. So what we see today is foils that might have 2 micron roughness, and I'll show you pictures of these as we go through. So again, just to show you what these kind of foils look like. So depending on what you are bonding to, you either have the matte side as the surface side, or you have the matte side eventually as the side that attaches to the laminate material. This slide here kind of gives you a better indication of how rough some of these foils are. So in all cases, the bottom side of these pictures would be what is exposed to the environment. So the top side would be what is pressed up against the laminate material. So standard foil would have a 6 micron roughness, and all those teeth that you see at the top there, top left picture, would be what is adhered to the laminate material. There's a lot of teeth there. That's great adhesion, but if you're looking at signal propagation through those teeth, not a great thing. We look at RTF foil, a little bit smoother. And again, the reason there is because they're bonding the matte side that comes out of that drum against the foil, and now we can control that roughness of the side that's exposed to us through subsequent processing later on. And then we get to VLP foils, which have less roughness, and there's different categories of VLP. So a very common VLP foil is a 4 micron roughness, but if you see a foil that's called VLP2 or VLP1, those numbers are the roughness numbers attached to that foil. So a VLP foil that is VLP2 has 2 micron roughness. And then finally, HVLP foils. You can see here where it's very smooth, both sides. And these foils here operate at around, and again, anywhere from 1 to 2 micron roughness, depending on the foil manufacturer and also the laminate manufacturer as well. And then just some quick numbers explaining all these different values. Again, we talked a lot about these different roughness values, reverse treat, very low profile, and ultra low profile. I do get asked for these numbers quite a bit, so when I do get asked, I present this chart to the customer. And then finally, on the foil side, our foil supplier will take these large rolls of foil. Now they will cut them and sell them to us as foil only, and we're going to take these foils and do our external layer press when we build the circuit boards. But they're also going to take these foils and send them to our material supplier for them to create cores for us as well. Next step we look at is construction of specific laminates.
Just before you get into that, Gus, I just wanted to ask a quick question to everyone, and I'm just wondering if this is their first PCB boot camp that they've attended. So I've launched that poll for you guys. Please answer, and you have 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. All right. Thank you, everyone. And it looks like this is only the first for about 38% of you. So thank you very much for joining us. And everyone else, welcome back. Continue on, Gus. Thank you.
Awesome. Thank you. Okay, if we look at laminate construction, so laminate, what we call laminate, is formed by combining those sheets of copper supplied to our supplier by the foil manufacturer, along with one or more plies of prepreg that our supplier is creating on their own, as discussed earlier. Those get combined in the lamination press, and then under heat and pressure, this prepreg will cure to a C stage or a final cure stage, and copper laminate is produced. And in terms of what it looks like, this is a very simplistic rendering of what it would see. There is a press. Typically, these things are pressed under vacuum to ensure that there's no air that's entrapped. And depending on the construction of the laminate material, there could be one ply of prepreg, there could be two, there could be multiple. Now, in some cases, customers do ask for 2 plies of prepreg. I will let you know from a fabricator perspective, single ply constructions are always the cheapest for us in terms of the cost of material. However, depending on whether you need a sense of a safety factor in the design and you may ask for 2 plies, or whether you're trying to combat signal integrity issues, you may also ask for 2 plies. We do get customers that ask for 2-ply laminates as well. General rule of thumb for laminates, which I don't show here, is if you are at 8 mil laminate thickness or below, we're going to use a single ply laminate. And then once you're above 8 mil laminate thickness, all laminates are 2-ply. It doesn't mean that below 8 mil, 2-ply is not available. It's just not the most cost-effective option for us. But we can supply 2-ply laminates anywhere from 4 mil to 8 mil thick. Okay. So again, these get pressed into a final, what we call a C-stage construction. And when we look at the, again, the direction of the material, so our material supplier will typically make rolls that are 50-inch wide. Then they get trimmed down into 48 by 36-inch trimmed values, which coincidentally fits very well with a typical standard master panel size for circuit boards, which is 18 by 24. So a 48 by 36-inch master sheet can get cut down into 4 sheets of 18 by 24 fairly easily. And then, of course, like we said, there's always a grain or a warp direction, and there's always a fill direction that we have to be aware of. So we have our laminates, we have our prepregs, then we have our foils, which are the basic building blocks for us. And again, they all get supplied to us at different stages. We then go ahead and we press all these together to create a final circuit board. And this is what a typical laminate would look like. In this case here, we have a 4-ply laminate cross section. And what we see is we see the copper foil, which is shown at top and bottom. we see the epoxy resin, which is the light gray area, hopefully in your pictures. And then we also have the woven fabric, which you can see goes in two directions. So the one that has the goes left to right would be one direction, and then you'll see a set of bundles that look like eye shape, and those are the same bundles that we're seeing, except these are now coming in the direction towards us. Okay, and again, that weave is present in almost everything that's built in terms of a circuit board material set. Now, a quick note on shelf life of these materials. So we do get asked about this quite a bit. So again, most PCB laminate materials are thermoset plastics, and this means that once they are pressed and cured, if we reheat them, it has no effect on their molecular structure. So you can't reheat them and have them melt. So this is different than thermoplastic materials, which can be pressed, cooled, and repressed again. So because we deal with thermoset materials, I always tell customers you get one shot to press it right, and if you can't press it right, or if something happens and the press breaks down, or you get a power failure, then you basically have to throw away that press load and then restart it. Now, once cured, these thermoset materials will have an indefinite shelf life, and again, as long as they are kept in some sort of storage where you're not at extremes, they can be kept in relatively uncontrolled conditions. So let's say the back of a warehouse, which may see, cold, heat, typically they're fine. Nothing's going to happen to these materials, and they do have an indefinite shelf life. On the prepreg side, because the prepregs are only partially cured when they arrive at our facility, and they stay partially cured until they are fully pressed and cured, they do need to be stored in a controlled environment. And again, controlled environment means controlled humidity, roughly around 50%, and then a temperature that is not going to have these things self-cure, because prepregs will self-cure over time. And because of that, their shelf life is finite, even if they are kept in a controlled environment. And useful prepreg shelf life is around 3 months from date of manufacture. Now, this is important to understand, because we do get requests for pre-ordering of materials, and just to avoid any lead times associated with that. So when you do have a requirement that requires us to pre-order materials for upcoming builds, if the schedule does slip, the material may become unusable, and then the cost of the material is often charged back to the customer at this point. So keep that in mind when we look at items like pre-ordering of prepreg specifically. Now, foils and cores, no issue. Okay, so those are the basic building blocks, and then we look at some of the properties of these things once they're all fully pressed and they're in use. So the first thing we look at, which is always on everyone's mind, is TG. And what does TG mean? So TG is the temperature at which the resin changes from a glass-like and relatively brittle state into more of a what I call a rubber-like state. And then, of course, that changes its mechanical behavior as well, and more specifically, the expansion rate. So when the material behaves like a glass below its TG, it expands very little in all directions. Once it goes into a rubber-like state, those expansion values will increase quite a bit. This is a fully reversible transition in nature, and unlike transition temperatures or melting temperatures for metals, for example, the glass transition temperature for a plastic material typically takes place over a wide temperature range. So pinning down a specific TG requires you to kind of look at a curve of how this material expands over time. And again, mechanical properties change, electrical properties change, and this is why it's important to understand what the TG of that material is. So here's a graph of the thermal expansion of any, well, there's a few materials listed here. Thermal expansion of the material in percent versus temperature itself. And that low slope graph at the bottom left of this curve is the pre-TG phase, and then once it hits that TG point, it starts to expand a lot more for every degree that we increase the temperature. And it's that inflection point right between those two curves. So if we were to draw straight lines between each of those curves, where those straight lines intersect is where that TG of that material is. Okay. Now, TG affects the expansion. So we define a parameter called CTE, and CTE is called coefficient of thermal expansion, and depends on a lot of items. So modulus of the components, the strength of the chemical and physical bonds, of course, and that's all, you know, some of the stuff that we work with. But the end result is we now have a material that expands a certain amount for every degree Celsius or Fahrenheit that we increase. And we have different expansion rates for each different dimension. So we have an expansion rate for the X and the Y direction. And generally for circuit boards, it's going to be around 14, 16, 18 ppm. And then we have a Z-axis number, which typically is going to be a lot higher than the X and the Y. And what happens in the Z-axis is your expansion rate can be anywhere from 35 to 60 or 70 ppm. And that Z-axis expansion is very critical for us because that's the one aspect that we see, or one parameter that we see is going to affect how robust our final circuit board is. And I'll explain all these as we go through. So in the X and the Y axis, we have these reinforcing fibers that will actually help to constrain the amount of expansion in that direction that the resin sees. So that glass reinforcing material keeps the expansion of the resin to around 14 to 18 ppm. And if we look at the expansion coefficient of pure copper is around 18 ppm. So now we have a material that's very well matched to the copper that we're also working with. Now in the Z-axis, and I show a picture of this on the right side of the screen on slide 42, there is no continuous reinforcing material in the Z-axis because we are stacking everything up vertically. So even though we have a reinforcing glass in the X and Y axis, in the Z-axis, there are areas where we will have pure resin only. And because we have pure resin only, that now allows the expansion in the Z-axis of the resin to expand at a much higher rate. And you're saying, okay, why is this all important? Well, we have vias and we have holes in the circuit board itself. And these holes tend to expand at 18 ppm. And now we have a material that in the Z-axis tends to expand in some cases up to 60 ppm. So now we have a mismatch between what the material wants to do and what the hole wants to do. And what eventually happens if the expansion is too much is we now have that hole barrel start to crack. And the cracking hole barrel now leads to a failure electrically in the circuit board. So working with materials that have lower TG, if you have lower TG in your material, you typically start to expand more at a much lower temperature. If you've got higher TG materials, you now have a greater or more robust window until the material starts to see its very high expansion rate. So we have the pre-TG expansion, which can be general operating conditions in terms of surface life. And then the post-TG expansion is what is a problem for us, especially in assembly, if that TG value is too low. So with assembly temperatures today in the 260 C range, we are going to be past TG of the material, but the question is, can we stay above it for as little time possible before we start to damage the material set? So CTE in relation to TG, in relation to the actual construction of the circuit board, becomes very critical for a material set. We also look at parameters like TD, or thermal decomposition temperature, and this is defined as the temperature at which the material degrades to a point where 5% of its mass is lost. So plastic materials, as you heat them up in temperature, they do tend to degrade, and when they degrade, they lose mass. So TD is defined at that temperature at which 5% of the material is lost. And what you see is for standard FR4, a typical TD will be around 320 degrees Celsius, whereas for a phenolic cured epoxy, and these are the ones that are generally used today, TDs are often in the 350 degrees C range. Okay, so understanding TD is important because the higher the TD, the more robust the material is from a temperature perspective. And then finally, we define an item called time to delamination. And there's a couple of parameters that we use. So we have a value called T260. And the test for this is you put a sample on a hot plate that's at 260 degrees Celsius, and you observe the time it takes for that material to delaminate. All right. And this T260 number used to mean something in the old days, and I'm talking old days, maybe 10 years ago, because you'd have materials that failed. But as material manufacturers got more advanced in their development of materials, all materials today essentially pass the T260 test without failing. And the test typically runs for about an hour. So if you can put your sample on a hot plate for an hour and not have it delaminate at 260, that's the max test you can run. So knowing that, they keep bumping up the criteria. So now instead of a T260 test, we have a T288 test. Same test, except now the temperature is T288. And the whole point of the test is to get a failure that's below 60 minutes. So you can characterize material sets versus other materials. So if all materials have survived that 60-minute test, the test is of no use to us. So the T288 test is a valid test, but we're also seeing materials today that can now withstand that for an hour. So the test that we look at today is more like a T300 test. So now we have the hot plate at 300, and how long does it take your material to withstand that? And we're not talking seconds in terms of these tests, especially the T300 test. We're still looking at roughly a 10, 12-minute test to failure. But if we look at parameters in general, between time to delamination, CTE, TD, and TG, those four specific parameters tend to define the mechanical aspects of the material that we're working with. And then just a quick note on sequential lamination. So for those of you that do a lot of HDI work, you need to understand that materials, even though they are cured, and we say that nothing really happens to them after they're cured, once we stick a cured core material or a C-stage material back in a press and we run it through another press cycle, the TG of that material does tend to degrade. And it's not uncommon to see the TG of a core that's been reheated drop by about 3 to 5 degrees C for every heat cycle that is seen by that core. And this is important when you get to multiple sequential laminations where you may have a core, especially a middle core, that's part of your first lamination cycle. If that core sees 3 or 4 additional heat cycles before we even ship it out for assembly, then that TG of that middle core may drop by as much as 20 degrees by the time it even gets to assembly. So keep that in mind. It's one reason why we don't have unlimited number of lamination cycles that we will do. So a lot of times we'll max out at about 6 or 7 lamination cycles before we say, okay, that initial cycle with the initial material sets at some point becomes compromised because we're just heating it up and pressing it too many times before it even gets out of our shop. On the electrical side, of course, there's always factors that influence decision-making on this side. From our perspective, what drives dielectric constant and loss tangent, which are the two main parameters for electrical on our side. The epoxy resin system is one. So what are the parameters of that system on its own? DK, DF. And then finally, the glass fabric composition. So I did mention earlier that glass has a DK value and a DF value, and then the resin has a DK and DF value. Now, the combination of those two and what parameters you get out of that is defined by the resin to glass ratio of the stack up. Now, before we get into that, we'll talk a bit about attenuation and loss and why that's important. So from a PCB side, we get a parameter called signal attenuation or loss. And what happens is you get a signal that goes into your circuit board, and because of the characteristics of the material set, whether it's copper or whether it's the material set itself, there's always some attenuation that occurs. And the factors that contribute to that are both from the copper and from the dielectric. And what we see is dielectric loss becomes critical at high frequency, whereas copper loss is the dominant parameter at low frequencies. But both are quite important from a PCB perspective in terms of understanding their impact on the signal integrity of that part. And then the other thing we look at is how signals, especially when you start to get to high-speed signals, your current density tends to change. So I have a couple of examples here of how current density changes from basically DC or very low frequency application. So that green is a very consistent copper density. But what we see as we go to higher and higher speeds, and again, this is only to 1 gigahertz, is we now start to see this current density tend more towards the outside of that trace. And in the case of the 1 gigahertz example we show, most of the current density now ends up being in the outer layer of that copper or the skin. And general formula tells us that 5 skin depths control about 100% of all that current. So why is this important? Well, now roughness comes into play. So we talked a little bit earlier about how we see these rough tops and bottoms of these copper foil features, and now your signal propagation changes because you either have a very rough or a very smooth foil. So understanding how skin effect or skin depth affects current density and how current travels through a trace is important. Now, one other note on this is finish starts to play a role as well, final finish. So we see a value at 1 gigahertz of about 81 microinches for a skin depth. So if we assume 5 skin depths contains all the current, we're at about 400 microinches total to contain all your current. Now, if you've got an ENIC board that has a very thick layer of nickel, that nickel layer itself might be about 250 microinches of nickel, depending on what we're trying to do. So there can be cases where you're expecting your signal to travel throughout the copper only, but because you have an ENIG coating on some of these areas, you actually have signal that's traveling through a nickel layer rather than a copper layer. So these are all things that you got to keep in mind as we look at copper roughness and also finish and how it affects current density on the electrical side. But going back to the glass versus resin interaction, when you look at a bulk data sheet from a manufacturer, what you'll see is you'll see a bulk value for DK and bulk value for DF. The fact is that value is not representative of what the material is really about, because depending on the construction of either a core or the construction of the prepreg in terms of glass style, the amount of resin, you actually will see a variable DK and DF value. And I'm showing here an example. This is an example for a very common FR4. It's got a 3 mil core as a construction option, but that 3 mil core has 3 different options. You can either have it with a 1080 prepreg, a 1086 prepreg, or a 2113 prepreg. And each one of those has a specific resin content. And because the resin content and that percentage of resin changes, you now get varying DK and DF values. And it can be quite substantial. So in this example here, I can go anywhere from 3.84 to 4.34 on a DK value, depending on what construction is used in that build. And it's important as you get to higher speeds, because one fabricator may use a core that is 1080. The same fabricator uses a core that's 2113, but they're both 3 mil cores. So they meet the intent of the design if you're speccing out a 3 mil core, but you're getting 2 vastly different constructions. So that always has to be understood as to what specific construction that core is, or that prepreg, in a design. This chart here, I call it my intuitive chart. As we go to higher resin content, the decay of all materials drops, and again, that's because the decay of resin ends up being around 3, and the decay of glass ends up being around 6.5. So the more resin you have in your construction, the lower the decay value that you'll see as an effective decay of that glass to resin composition. So we talk a lot about FR4, but as we get to the need for higher and higher speed and lower loss and lower decay, we now have different resin options as well. And we see the phenolic filled epoxies, we see modified epoxies, something called PPO or polyphenylene type glass. And then we start getting into the more exotic stuff like hydrocarbon ceramics and PTFE glass fibers. So on this chart here, just meant to kind of show you the different options available as a broad snapshot, and then just typical applications where you would see all these materials being used. So for example, on the Teflon side or PTFE, you're seeing a lot of those for microwave applications, for antenna, for radar applications, especially with automotive today. And then as we go down the line, we see the PPOs and the modified epoxies being used a lot for high-speed digital type of applications. And when we say high speed, you know, it used to be 30 gigabit, then it's 50, now it's 100, and of course that keeps going up. So as they keep going up, we get more and more materials being created by our suppliers that are trying to fit the requirements that are needed. And like I mentioned earlier, if you have the perfect world of traces being routed at a 0 and 90 degree angle, and then we have the material that we supply at 0 and 90 degree angle, you can now have traces that run perfectly up against fiber bundles or gaps. And there's ways around that. One of the ways is to rotate your traces or to route your traces on a different angle. Or the other way around that is to try to rotate an image on our panel, or try to change how that material is ordered by us or from our supplier. Again, as you get to higher and higher speeds, you want to break that consistency or the alignment of the trace to the fiber weave. And what we see is that a 10 degree offset between the two, no matter which way you do it, whether it's material related or routing related. Once you get to about 10 degrees, you've now broken that that alignment that you see that tends to give you signal integrity issues from an electrical perspective. And aside from that, once you go into really high speed materials, they start to move away from that glass mat altogether. So the anisotropic laminate, which is the bulk of what is produced today, because it's also the cheapest, that's the laminate that you see there on the left. And then as you get more towards the Teflon, PTFE materials, what you'll see is they get away from the oriented glass mat into more of either a random glass mat or no glass at all. And no glass at all is great for signal integrity, but it also makes it very difficult for us to build with these materials because they tend to move a lot, and it's tough for us to maintain registration. So glass helps us from a fabricator perspective in that it controls movement, but in some cases it's not always desired from a design application perspective. Okay. And again, once you've got your random strands, it doesn't matter if you're orienting your traces one way or another way. These examples show that no matter which way you do it, the traces, and this is a differential pair, it's very consistent in terms of what it sees underneath from a resin to a glass perspective. One last note on the higher end stuff is most of these high end materials, like these Teflons and ceramic materials, they will not have an associated prepreg that's made out of the same thing that would be for like an FR4. So they actually require what's called a bonding film. And some of these bonding films end up having properties that do not allow us to press these in a standard PCB press. So when you look at these great materials and they're like, oh, I like this Rogers 3003 material set, it's great. understand that if you're making a multi-layer, at some point you need some sort of a bond film, and that bond film is not going to necessarily match that high-end laminate in terms of performance. And this is all something that we could help you with. So if you do have questions from a design perspective, we always say reach out to our FAEs. We've had the benefit of inventing the wheel with someone else. So there's no need for you to have to reinvent it from your side if you're going down this path of RF or microwave type material sets. And lastly, I know we're running out of time. I have a few slides here on hybrid construction. So these material sets that are high end can get very expensive. So one way to go around that is to create a hybrid where you have one core of the high-end material, like a very low-loss dielectric or a microwave material set, and then you can have the rest of your structure as FR4 if that's what you need, and that helps to mitigate the cost of the entire build. And of course, what it also does is it creates some problems for warpage, but again, in some cases, you're kind of constrained by having to go down this path for cost, so you need to live with a little bit of warpage in that final product. And my example here just shows in the top right, it's a cross section of a high-speed laminate on one side, and that would be an RF or a microwave type application. And then underneath, where you may not require the high-speed material set, you can have standard FR4, and we'll build that as a hybrid. Just a note here, not all materials are compatible. So always work with us, especially if you have a multi-layer, multi-material application that you're looking at. Like I said, some of them work better together than others. And then finally, just a note on these material sets. If you're looking at HDI, you tend to have to design with wider microvias if you're going from layer 1 to 2, for example, because most of these high-end laminates that's shown in light blue here, you are not able to get them thin enough to allow for thin microvia. So some of them start off at 5 mil minimum thickness. Some of them start off at 10 mil. So if you have a 10 mil dielectric that's required on one side, what ends up happening is your minimum hole size, if you're doing a microvia 1 to 2 for HDI, is going to be about 12 mils minimum. Okay. And again, work with us. We can guide you down the safe path of design. So finally, a summary. So we talk about how to specify these material sets. And we always get asked this question. So there's 3 ways to specify. One is to dump a bunch of material properties in your fab drawing, DK, DF, TG, CTE. That's great, but I can give you about 40 materials. If you give me a requirement for each of these parameters, I can give you about 40 materials that meet your requirement. So it doesn't really narrow it down a lot, but it is a good way to kind of leave it up to a fabricator to pick the most cost-effective option if that's what you're looking for. The next one up is the IPC slash sheet, which is this guy here. And with the IPC slash sheet, you kind of narrow down your requirements based on IPC 4101D. And that narrows it down to, let's say, about 10 material sets that would be compatible with what you're trying to do. Might be good enough for you. It just narrows it down, makes it a little bit easier for us as well. But as you get to much higher speed designs or designs that cannot afford to have variation from fabricator to fabricator, then you start to supply us with documentation that shows the material set, the glass style of the prepregs or the laminates, number of plies, and you get into a much more detailed requirement. Now, as a fabricator, we don't like that because it really ties us down. But from a design perspective, it may be your best bet to ensuring that your design can be manufacturable at different fabricators, at different locations, with a decent level of consistency in the final product. So option number 3, great for you guys, not great for us. But if you're looking at option number 3, always try to work with a fabricator first, because that's how you're going to define the stack up that at least you know is going to work for at least one fabricator. If you try to do this on your own, working with unpressed thickness tables or materials that may not be available at a fabricator, you will run into trouble at some later point. Finally, so we kind of talked through all these. I'll summarize today's webinar. Laminate materials consist of a resin system and reinforcing material, typically glass. And again, it could be ceramic, could be glass microfibers, but that's the basic constituents of what a laminate is. It has properties which play a huge role in the final properties of the design. And these are all, again, based on resin ratios and reinforcing materials that are being used. We have specialty laminates that can be used, but these are also can be difficult to work with or difficult to manufacture. So always understand the limits of the high speed or high frequency stuff. Always take care of how you specify materials so boards can be consistently made from lot to lot and from fabricator to fabricator. And again, I don't have it on this slide, but I always say if you're not sure or for best practice, always consult with your fabricator ahead of time to ensure that you're getting stack ups and design rules that are going to be manufacturable from your side on your final product. That's all I had. Sarah.
That was great. Thank you so much, Gus. Well, I know we're out of time, so I'm just going to say the closing remarks, and then if anyone would like to stay for a couple questions, please do. So thank you again so much for joining us today. If you thought this was a valuable lesson, or session, wow, sorry, please feel free to visit us at ttm.com/events/training online or follow us on LinkedIn. And we have other topics, because we have other topics presented monthly. Our next webinar is Rigid Flex in May, and then we'll cover via treatments in June. We'll hope you join us and share with colleagues. So we'll get into a couple of those questions quickly, if you are able to stay with us. Gus, the first question we have for you is, for a multi-layer PCB, what would be a typical thickness tolerance that could be expected? Is it usually on the plus or minus side?
So we always work to a nominal, and we need tolerance on either side, depending on how these things are pressed. So a typical tolerance that works for everybody, when I say everybody, I mean fabricators, is plus or minus 10%. And I know the plus minus 10%, not always possible. Depending on the fabricator, you can ask for a tighter tolerance. The tighter tolerance you ask for, the more difficult it becomes to meet, and the more pilot runs or pre-processing that's required in order to see if it's possible. So some of our facilities can offer plus or minus 5%. It does come with a cost in some of those cases.
Great, thank you, Gus. A few people are also asking, what is skin depth?
So skin depth is just the distance at which we measure the current flow. That whole skin depth discussion and the whole SI discussion probably requires its own webinar. So I'm going to leave it at that. If you do have questions, I would say, or if you want to discuss it further, send that off to Sarah, and then we'll go offline with questions about skin depth.
Great. And our next question we have today is, well, if we use different pre-preg materials, like a hybrid stack-up, and same board, will they affect to CTE and reliability? For example, Rogers and outer layers and F4 and inner layers.
Yes, so they do. So, and that's one thing that we always have to be aware of, is the CTE of different materials will affect the overall CTE. And again, this is where we have knowledge of combinations that work. We have knowledge of combinations of materials that don't work. But yeah, it's a concern. And if you do want to go down that path where you want to mix material sets, please contact us, because again, not everything is possible, and some options are a lot easier than others.
All right. Our next question, and this will be our final question, and then everyone else who may have had one, we will send you an email shortly afterwards to get that answered for you. And our last question is there any way that the shelf life of pre-preg can be increased from 3 months?
So that one's an interesting one, because it depends how much risk you want to take. So generally, after a certain point, the prepreg is not usable. So whether it's 3 months or 3.5 months or 4 months, you know, it's possible, but we're trying to ensure that we have a robust product that we're building for you. So you want to stay at something that's not too crazy. So that's where the 3 months comes from. Is 3 months conservative? It is in a sense, and we could, in some cases, make exemptions and kind of go a little further with some recertification. But in most cases, you want to stick to 3 months or below for that.
Great. Well, thank you again, everyone, for joining us today. Be sure to follow us on LinkedIn, and we will get to you shortly with those other questions that have been asked. Thanks again, and have a great day.